It gives me very great pleasure to introduce Dr. Rajesh Dakal. Rajesh is an Associate Professor of Structural and Earthquake Engineering here at the University of Canterbury, and he's a Chartered Professional Engineer in New Zealand. Rajesh led several building assessment teams following the Canterbury earthquakes and was a co-recipient of the 2011 Institute of Professional Engineers President's Award for his contribution to the post-earthquake recovery. Prof. Dakal also received more than a dozen other awards, including the prestigious EQC New Zealand Society of Earthquake Engineers, NZSEE, Ivan Skinner Award for the Advancement of Earthquake Engineering Research in New Zealand, and also the same body awarded him the Otto Glogau Award in 2007 and 2011 for publishing outstanding technical papers in earthquake engineering. Rajesh has authored more than 200 papers in different aspects of structural and earthquake engineering, and he's internationally recognised for his expertise in this field. He serves on various review panels and is an associate editor for the Journal of Structural Engineering, and he serves in the editorial board of 4 other international journals as well. In New Zealand, Rajesh is on the national panel for the 2012 performance-based research funding, which all universities are really waiting for the results because we'll get some money, we hope. He's also an elected member of the management committee of the New Zealand Society for Earthquake Engineering, and he convened New Zealand's biggest ever earthquake engineering conference in Christchurch in April 2012. It gives me great pleasure to introduce Rajesh to you now, who's going to present his talk. If you can pick his microphone back up, that's just fallen off his shirt. And when he's fixed it again, we won't be a minute, ladies and gentlemen. Did you know this space used to be a bicycle park? Look at it now, isn't it beautiful? Here it is, Rajesh.
Oh, thank you very much. I hope everyone can hear me. Yeah. So thanks, Jen, for that kind introduction. And it's indeed a pleasure, great pleasure to be in front of you and sharing what I have learned over the last decade and a half in relation to earthquake engineering. And that was a great opportunity for all of us. Of course, we all regret those lives lost, but otherwise, actually, it was an opportunity for us to actually test whether what we had learned over the last couple of decades, whether all those things made sense or not. And based on my understanding of earthquake engineering as a science and what we experienced over the series of earthquakes in Canterbury, I'm going to present what I think is the need for future. Okay? So the topic of my talk is what if we could minimize financial loss from earthquakes? So before I go any further, first of all, as I'm going to refer back to the seismic design principles or earthquake-resistant design principles, quite often it's better to have a quick look at what actually seismic design does. So all these seismic design philosophies throughout the world, wherever you go, the guidelines there are driven by few principles, and those principles are given here. So the principle is we require immediate occupancy of our structures, which means no disruption of service after small and frequently occurring earthquakes, which means the building, if we apply it to building, the building does not need to be closed for repair, but it does not require us to have a building completely undamaged. You still can have a damage which will not require the building to be closed and satisfy the design requirement. Similarly, at the other extreme, what we have is collapse prevention in large and rare earthquakes. Okay? The largest possible earthquakes, if that occurs, still the collapse of a building or any structure should be prevented. Those two are the underlying guidelines. And several codes, they have an implicit requirement in between. Some codes do use that, some codes don't. And that is reusability or repairable damage in moderate to strong earthquakes. Okay? So that means you might need to close the building for repair for few days to few weeks, but the building should be reusable, repairable, right? In New Zealand, we have got what we call a design basis earthquake, a level of earthquake intensity at which we design our buildings, and that goes somewhere here in that spectrum. And what we require life safety in that level of earthquake, design level of earthquake. So with that background now, you all should be able to relate back to, or at least understand better what I'm arguing in the coming slides, okay? So with that background now, let's have a quick revisit and summarize the main features of building damage caused by recent Canterbury earthquakes. So first of all, let's zoom into that category, old and unreinforced masonry buildings. What did we observe? We observed that a lot of those buildings damaged very severely, even some retrofitted buildings, they incurred severe damage, and that included heritage buildings as well. And there were some buildings which completely collapsed, and a sight of buildings severely damaged in a row across a street was not uncommon in the CBD area after those earthquakes. So of course, I'm not going through the details of that, but based on what we observed, what could we conclude for this building category type? Extensive damage to old buildings in general. Many unretrofitted, unreinforced masonry buildings in the city flattened, they simply collapsed. Most of the remaining old unreinforced masonry buildings were very severely damaged, which were not technically feasible to repair. So that resulted in a current situation where probably in the CBD we will not see any old unreinforced masonry buildings left after the CBD is open, if ever. So let's go to the next category, modern commercial buildings. There are several examples. When I say modern, in the last decade and a half since our modern design code has been established. So the buildings designed by the modern capacity design-based principles. Okay? So when we look at that, we saw most of the buildings, they are standing there from outside. It doesn't look like severely damaged, but when you go inside and take out the ceilings, or carpets, and then you will see a lot of damage in different components, okay? So components such as the damage in frames, columns and beams, or floors even, and then in some other buildings you'll see damage in walls, structural walls, damage in the columns, damage in the floor, right? And other buildings, damage in the staircase. So several different types of damage in that class of building, and some of the damage were caused by vertical acceleration effect, because we all know that the level of vertical excitation in the earthquake was really high, actually almost unprecedented in any other earthquakes. Okay? So with that in mind, now what could we conclude? We could conclude that most modern buildings built within the last 15 years suffered damage of different extent to different components, staircase, column, beams, frames, floor, walls, but none collapsed. Despite the severer than designed for ground motions they were subjected to, several modern buildings were technically repairable. And I do repeat that, they were technically repairable. A lot of those buildings were decided against repair due to other reasons. Financial viability, the negotiation between the insurance companies and the owners, and many other reasons. Technically, it was possible to repair many of those buildings. So now, the third category that I want to go is actually performance of secondary building elements. When I say secondary, actually in a building, there are components which carry the load. The load that we are putting on the floor, it goes to the beams, the beam transfers it to the columns, and the column transfers it to the foundation. Foundation takes it to the soil. These are structural components. Whereas the partition walls, ceilings, the facades, windows, they are not transferring the load. They are there because they are required for other purpose, okay? So they are called the secondary elements or non-structural elements, and the damage was very severe. You could have seen those sides of chimneys falling off the roof of several buildings, and they are non-structural elements. Parapets falling down, they are non-structural elements. Canopies falling down, non-structural elements. Ceiling damage was a very common sight in most commercial buildings and many residential buildings as well. Facades, internal walls and linings, so much damage. Windows, so much damage. And contents, racks, shelves, and the things lying on the racks and shelves. severe damage to those parts. Okay? So they do not make the building irreparable. Regardless of how much damage you have got in your non-structural components, you can still easily repair the building. Okay? Because they are not required for the structural load transfer path. So now, with these in mind, if we don't just concentrate on loss, if we look at life safety as well, these non-structural elements and contents, the damage to them actually could have been a big risk in terms of life safety as well. So you can easily imagine people being, like hit by those falling heavy racks with full of books that could have easily fallen on top of someone. That ceiling completely, because we experienced, or we saw that in our lecture theaters, 7-meter high, those each ceiling panels, they weigh about 15 kg. So when 15 kg ceiling panel falls from 7-meter high, the student sitting in the classroom, severe injury at least, if not life threat. Okay? So similarly, that whole part is falling down. So these things, they are not only important for loss, but they are also important for life safety. Okay? Even if life safety is the criteria, there is no justification to ignore non-structural elements. Now, what could we conclude? September earthquake, severe damage to non-structural components. Note, modern buildings suffered only minor structural damage, whereas the non-structural components suffered severe damage. And in February earthquake, major damage to collapse of non-structural elements, when the modern buildings suffered only moderate to severe damage. Okay? So what that means is there is clearly a mismatch between the performance of structural system and non-structural component in modern buildings. So non-structural and content damage contributed significantly to the financial loss. You could relate this to your own house, probably my house. I have no structural damage in my house. I have been living there for the last 2 years without any repair, but the EQC says that the repair bill is going to exceed $25,000. Okay? So that is all because of those few cracks on the walls and ceilings, which are not structural components. Okay? So they contribute quite substantially to the financial loss. Now, summary of observation from Canterbury earthquakes then. Older and unreinforced masonry buildings severely damaged and some collapsed. Modern buildings did not collapse but suffered damage of varying extent. Severe damage to non-structural components and contents. Ground response was very poor in many parts of the region due to liquefaction and lateral spreading. Many buildings were rendered uninhabitable due to ground foundation damage and huge financial burden to the economy. So those are the major summary of what we observed. Now, let's ask the question, did we expect this? Before we answer that, we have to keep this in mind. The ground motions were similar to in September earthquake and severer than in 2011 February earthquake, the current design level ground motion intensity. So once we keep that in mind, then let's start answering those questions. Damage to modern building, did we expect this? Yes, because those buildings were never designed to sustain that level of shaking. Okay? Now, severe damage and some collapse to older unreinforced masonry buildings, did we expect that? Yes. Perhaps we were very lucky that more did not collapse. And that was mainly to do with the short duration, because we witnessed a lot of buildings, old buildings, in a stage that they couldn't have probably sustained another 5 seconds of severe shaking. Okay? Damage to non-structural components and contents. Did we expect that? We never thought about this. The earthquake engineering community has been completely unaware of this fact. They have never brought this into the design framework. Very poor ground response. I'm a structural engineer, not a geotechnical engineer, so I don't know where the solution is. So I pose the question, did we know this? If we knew, then why did we let the buildings be built on those areas? Okay? Now, the last huge financial loss, we never considered loss in our decision-making process. So with that, why loss is not considered? Why damage is the main focus of different people? So loss versus damage, that is an enigma. If you look at that, given the ground motions were very much severer than that used in design, the extent of damage was smaller than what the engineers expected. And now look at another statement. Given the buildings were designed for earthquake resistance by competent engineers, the extent of loss was greater than what the public expected. And they both are right in their place. So that has forced me to wear two hats. If I wear the hat of the engineer what I would say, in general, the performance of buildings in Canterbury earthquakes exceeded the industry expectations. Yes, that's right. That's a correct statement. And then, when I throw that hat off, put the hat of a citizen, then I ask that question, really? The earthquakes have cost us $30 billion. That is 15% of our GDP. Did we expect to lose more than this? Do we really need to go broke before we realize, we admit that we haven't done well? And I'm right there as a citizen. Okay? So now, what makes a performance acceptable then? Engineers have been thinking life safety, that is it. Public probably are more leaning towards minimization of loss. So if it is less damage, if that makes the performance acceptable, then if you look at those design principles, modern design principles, that expects, I would dare to say, even attracts, that invites damage. Okay? And the ground shakings generated by these earthquakes were not smaller than what we design our buildings for. So even in that design level earthquake, the modern design attracts, accepts damage. So these shakings were bigger than that. So obviously, there is no place for us to complain as engineers. Now, do we think that less financial loss is what makes the performance acceptable? In that case, current design cares about life safety but not any other forms of loss. So if loss hurts or matters, then the design process should explicitly aim to control this, which is not happening. Okay? So now, what are the things we need to do differently from here on? Then, so we definitely need to have local soil characteristics to be checked thoroughly before building consent is granted on a new site. Non-structural components to be systematically designed for seismic resistance so that we can minimize loss. Stricter regulations on retrofit of older buildings, otherwise they will serve as graveyards again in another earthquakes, which only have the question of when, not if. So, communicate better, interact more among ourselves, among the engineers, among the architects, structural engineers, and geotechnical engineers, so that we know each other's limitations and expectations. Okay? And more important, with public, because public had the impression that when we say design for earthquake resistance, they thought that meant earthquake proof, which is not the case. So as engineers, we have not communicated well with the public. Now, adjust the design target according to expectation. If we expect loss to be minimum, then we need to have that in the target itself. We cannot sow something and then expect something else to grow out of it. So those need to be compatible, right? So now, what are the research needs that enable us to do things differently then? The research needs are, for existing buildings, what we need is reliable retrofit guidelines and enforcement policies. For new buildings, what we need is low damage building technologies for all types of buildings. Damage resistant design for non-structural components, ceilings, facades, partitions, parapets, all those things. Reliable ground assessment and mitigation methods, and then development of loss-based seismic design guidelines. So those are the things that we need, but I have another question. Can we apply them separately? And my answer is no. Why? Let's look at some examples. For example, what if a building is designed such that the structure, which is the frame, load-bearing walls, and floors, is damage resistant, but the non-structural components are very fragile? Then, let's look at some of the studies that we have done. When we look at the loss coming out of a building, depending on different type of uses, that is an office building, hospital building, hotel building, depending on the uses of different types of buildings, if you look at the contribution of different types of loss, that is the structural loss is only 18%. 62% is non-structural loss, and 20% is the contents loss. So similarly, that value, 18%, goes down in other types of buildings. Hospitals, because the contents are so valuable, those machines or those equipments are really, really valuable. So the content contribution goes up. And even our own study at the University of Canterbury, my colleague Brendan Bradley, who was a PhD student of mine, he did a detailed study, and we found that even for New Zealand scenario, if we look at the uses of the building in New Zealand, we find that only about 25%, 14 plus 11, of the total loss comes from structure. So now, if we use that low damage structural technology, then what happens? What happens is all our efforts may save only a small portion of the total loss, because we are not attacking the majority of it. Majority is 75%, which comes from not from structure. Okay? So think about Christchurch houses with little structural damage but with substantial insurance and EQC claim, right? That's the example of my house which I gave you. No structural damage, but the loss is still substantial because, and even if I had better structural technology there applied in my house, wouldn't have made much difference in terms of loss. Hence, for loss minimization, non-structural components and contents should also be designed for damage resistance. Okay? Now, let's look at the second example. Example is now soil-structure interaction. We have a building, we have a soil, we have foundation, and bedrock somewhere deep down. And when the earthquake comes, the load starts there, the action starts there, because earthquake is simply about shaking of the earth. And that starts at that bedrock, and then after that, it moves upward through the soil to the foundation, and through the structural system to the floors. And that's where things start getting thrown away, because that is the response, not the action. The action happens here. Okay? So soil is an integral part of that load path. So now, with that in mind, let's apply our chain theory, which is very common and fundamental principle in structural design. So what does that chain theory do? Basically, if the whole building foundation soil system is idealized as a chain, if that whole thing is a chain and earthquake is the force, then that force has to be taken by and safely transferred to the next component in that load flow path. Okay? So each of these links of the chain, they are those critical elements of the load path. So soil obviously is a critical element there, right? Now, the chain is as strong as its weakest link, right? Absolute strength is not important. Strength hierarchy is. Which is weaker than what? That matters more than how strong each link is. And it is a waste of resources to try to further strengthen the stronger links. So regardless of how strong you make that chain, that link, still the chain failure capacity will be dictated by that. So it is a completely waste of resources, right? So now let's apply that principle and see. If the soil is the weakest component, then there is no benefit of designing a building that can sustain a bigger shaking than the soil. The soil will fail anyway. That is the chain theory. So now, if we just concentrate on building without giving any due consideration to the soil and design the building for required capacity, that doesn't mean that the building is safe because it is a system. The load doesn't come directly at the foundation of the building. It comes at the bedrock and then gets transferred to the foundation through the soil, which also has to be able to take that. So now, this cries for a system design approach. So what would be a typical system design approach be? For the design level earthquake, the earthquake for which we design, or ground shaking for which we design, check the soil capacity. Our geotechnical engineering colleagues would have already calibrated at what level of shaking, what type of soil, clay soil, sandy soil, would liquefy or would start spreading. So there should be a relationship like that. And that will give us the approach, the method or the tool to check that. For the design level earthquake, check the soil capacity. First, if the soil is strong enough, then allow a building to be built there. If not, if the soil is not strong enough, first apply measures to enhance the strength or stiffness of the soil to the required level. Otherwise, it's useless. It's useless designing the building for the required design level earthquake. Otherwise, premature soil failure will make the building uninhabitable after an earthquake, regardless of how strong the building is. Right? So that's the framework of the unified design approach. Hence, to achieve a cost-effective and low-loss building system, what do we need? We do not need those things applied separately, but applied all together. Otherwise, we don't get the cost-effective system. Okay? So now, how has the ongoing ductility-based capacity design performed them? So immediate occupancy in minor earthquakes, that was number one requirement in the very first slide. We achieved that very frequently. But minor damage needing repairs without disruption, that will still satisfy the criteria, but we cannot rule that out. Reusability in moderate to strong earthquakes, that is also achieved, but moderate to severe damage resulting in injury and disruption of service, which is called downtime. And life safety in very strong earthquakes. And I can confidently say that the modern design, what we are applying now, if that is applied appropriately, 99% confident that life safety will be achieved. And that's what you'll see in last many earthquakes throughout the world. The modern design buildings, that has resulted in a very little number of casualties. All the casualties are either originating from unengineered buildings in developing countries, in third world countries, or old unreinforced masonry buildings in developed countries. Okay? So, with that, what we see, damage, downtime, death or injury. That is what we call 3Ds. Damage, downtime, and death, and they are the source of the loss in an earthquake. Okay, so where do we stand? We achieved all design objectives as I showed in the previous slide. We wanted from our design method, yet financial loss due to the 3Ds, damage, downtime, and death, could not be avoided. That's the data of loss that we suffered from last few earthquakes, and you can see the Canterbury earthquakes, 30 billion has exceeded. That's what I heard. Now, is this what we wanted? Even as the designer, even as the engineer, I would have to, if I'm honest, I would have to say, no, this is not, this was expected from the design code or from the design philosophy, but this is probably not what we wanted. And where have we missed the boat? We have missed the boat in setting the performance objectives for our structures. So now, where to in future? What do we carry on doing the same thing again, or do we do things differently from here on? So in the future, loss-based design has to be there. We have to apply loss-based design which tries to minimize the loss. So let's say loss optimization seismic design, right? So the performance objective number 1, life safety. Of course, we cannot compromise that. Still, regardless of how much it costs, life of people, that is dearer than any loss. So we don't want to mess up with that, so we retain that. But after that, once that is achieved, nothing else should matter. Whether it is immediately occupiable or whether it is repairable or not, that shouldn't be the criteria. Number 2 criteria should be minimization of loss. However you can achieve it, achieve it. Okay? Because that's what matters. For us, people shouldn't be killed and then loss should be minimum. Okay? So now, what is the design criteria for that design philosophy then? That should be expected loss in an earthquake should be less than acceptable loss by the client, by the owner, by the society, by the community, by the country. Okay? See, whatever is acceptable to us, the loss should be less than that. So now, what we need is actually, we need a probabilistic loss estimation methodology for that. And we do already have that. We are just in the process of simplifying it so that designers could use it in future, near future. Okay? But currently the method just does that. In very simple layman's term, risk is a product of probability and consequence. Probability of something happening or probability of an earthquake happening, and then what is the consequence, what is the likely loss from that earthquake. When you multiply that, that is the financial risk. And when we show that in graphical form, that is your return period of earthquakes. So return period is increasing in that direction, which means the earthquakes are larger in that direction, smaller in this direction. And that is the consequence, which is loss. Now, when we do our calculation, what we will get is, for larger earthquakes, obviously the loss is larger. For smaller earthquakes, the loss is smaller. Each point shows likely loss when an earthquake of this return period strikes. And now, when you go to this side, that is smaller return periods, which means smaller earthquakes, more frequent earthquakes. Smaller earthquakes, smaller loss. When we take the area of that whole curve, that gives us a measure of total seismic risk. What we in engineering terms also call is expected annual loss. And that is a direct measure of insurance premium. If you take off the overhead and profit, the direct insurance premium cost, which has to be proportional to the risk, that is it. Okay? And this process can cover all 3Ds, damage, downtime, death. We can directly do that for downtime as well. Only thing is, in terms of, rather than dollar value, it will be number of days of closure. And how many days of closure it is likely to be closed. And then the client can convert that. Okay, in each day I was earning like $20,000. So for 1 week it is 140,000. So you can convert that ultimately, right? Now, if you look at that curve and actually try to dig deeper to find out what's happening, what is contributing to that risk. This is a typical curve, and for example, the value, the expected annual loss is 0.35%. What that means is for a $1 million value, it is on average $3,500 per year. Sometimes you might not get any loss for 10 years, and in 11th year you might get 35,000. Okay, but it is averaged throughout the per year. And then when you look at different bands, okay, this is a little bit mathematical now. This is logarithmic scale. That's why, in fact, this distance is 10 times bigger than that distance. In logarithmic scale, you don't see that. That's why when you look at this area, this black area, it comes out to be like that. And this yellow area, it comes out to be like that. Because why is that black area bigger than the other? Is because that is logarithmic scale. Actually, that base is 10 times larger than the previous one, okay? So now what it is telling to us is out of that EAL 0.35%, 0.18, half of that almost, right? More than half of the total risk is coming from that small to moderate earthquakes, which has return period between 10 years and 100 years. Inverse of that is return period, right? So now, that is frequently recurring events with small cost per event, okay? In comparison to other earthquakes, okay? Now, if you look at that, a part or whole of this is insurance deductible because each event is small, and in that small event, for each building, the owner might lose, might require $1,000 to do some patch up. And your insurance policy, if you look at that, it has got insurance deductible, which we call excess. The first $500 of your policy, regardless of how many times that happens, even in your car insurance, right? Regardless of how many accidents you have in a year, for each individual claim, the first few $100 you pay. And by doing that, the insurance company is passing a huge amount of that risk to the owners smartly. Okay? So that a big part of that is insurance deductible. Now, if you look at the larger earthquake, that is actually from 100 years to 1,000 years return period. If you look at that, the contribution is 12 out of 35, which is about 1/3 of the risk. And if you look at those big events, of course, they have huge consequence, but the probability is so small. When you multiply probability with consequence, that gives you the risk. So that risk comes out to be small because probability is so small on an average basis, okay? So that is a very small contribution to the total risk. Now, what does that lead us to? It leads us to another term called expected lifetime loss. In annual loss per year basis, if that is the loss, then when you keep on accumulating that over years, throughout the lifetime of the structure, you will know over the lifetime of a structure how much money you are likely to lose, okay? And if you don't take into account any interest rate, just keep on accumulating the expected annual loss, of course it will be a straight line. If in 3 years' time it is 3 times the expected annual loss. But we have something called the net present value because $1,000 10 years later is not equal to $1,000 now. It is less than that, right? So if you take that into account by taking into account some interest rate, then your curve goes like that. That is your cumulative net present value of your earthquake-related lifetime loss. So let's look at that now. How does that help us to make efficient decisions? A couple of questions I'm asking there is a retrofit economically feasible? Or is the extra cost for low damage design financially justified? Let's try to ask that question by doing the life cycle cost analysis. Let's say that red curve is the curve, the expected annual loss curve, which we saw in the previous slide, without any retrofit. Now, there is a retrofit option for us, given by a designer, which costs, let's say, about $40,000 upfront at the beginning. But obviously, once you retrofit it, its annual risk goes down. It is more robust than what the structure was previously. So your expected annual loss will come down. So because of that gradient, that rate of increase of that cumulative loss goes down. And that blue curve, which is with retrofit, will cut that red curve somewhere. And what that gives us is actually, that gives us the time until retrofit is feasible. So if you want to use that structure for more than that 17 or 18 years, then your investment is justified. Otherwise, it is not. If that is the case, then what you do, you look for a second option. There might be another retrofit option which might cost $80,000. So it will start from there. But your curve, cumulative curve, might be flatter. It might cut off earlier. So very handy economic tool. So now even in terms of low cost technology, like for example, you base isolate your building. Base isolation costs you additional $50,000. Do you do that or not? What you can do is, without base isolation, what is my expected annual loss? With base isolation, obviously, your performance increases. What is your expected annual loss? And then you will get these two curves. You can compare, hey, my lifetime of the expected life of this structure is 50 years, and I'm getting break even in 10 years' time, so it is a smart investment. That's how you can make the do, okay? So that is in general. Now, let's look at how can we optimize the loss. So this curve shows you annual probability of earthquake and the probable loss consequence in terms of that damage, downtime, death, or injury, right? When the earthquake is small, damage kicks on. Damage starts happening, some few minor cracks and things thereabout. And as the earthquake size grows, downtime, the need for the building to be closed for repair, that starts quite later. And then, as you go really large, big earthquakes, then injury and death starts kicking in. Okay? So those are the conceptual nature of the three losses. And you might see that strange shape. What is that? That is actually when the damage happens such that the repair cost is more than 50% or 60%, the owner or insurer will make a call then saying that, hey, it's not worth putting that money and repairing that building. Rather than that, I'll demolish it and then repair a new one or build a new one. So once that 50-60% value, that decision cutoff value kicks off, suddenly the loss goes to 100% because you decide to demolish the building. Now, let's look at three bands. One band here, smaller earthquake, moderate earthquake, and large earthquake. And let's look at what contributes the most. In that high probability, which is smaller earthquake, you'll see there is no contribution of death or injury. Very small contribution of downtime. Most of the loss, whatever it is, might be smaller value, but it is dominated by damage, the repair of the damage. And in the medium one, the downtime kicks off. Downtime starts to dominate. Injury just starts because of only small probability. And in the low probability, means big earthquakes, your loss and downtime, damage and downtime, that hit 100%. Because as the building is not repairable, then basically the downtime is infinite. The 100%, the maximum possible time is the downtime because you have to demolish it, build a new one, and then only you start getting the service. Whereas damage also, as you are going to demolish it, 100% damage, 100% of the building value. Whereas substantial contribution from death. Now let's look at it in terms of strategic point. That part is low annual probability, means large earthquakes. So low probability, but very high consequence. And that is where the life safety, threat to life safety and injury comes mainly from, not in that part. So that's why we don't want to mess up with that part. We still, regardless of how much money it costs, we still want to retain that assurance to life safety. Okay? So we do that. Whereas, let's look at this part. Small to moderate earthquakes, which happens more often than those big life-threatening earthquakes. And that's where a lot of loss is coming from damage and downtime. So even if we mess up with that, we are not compromising our life safety. Okay? So that's where we have to attack as an engineer. We have to develop technologies which takes care of, which minimizes that as much as possible. Okay? And that's where the innovative technologies could come in, which avoids damage, because currently the perception is loss is proportional to damage. If we reduce damage, obviously we reduce loss. Okay? But the relationship might not be a straight line, might be a little bit complicated. Let's not go there. So now here, the idea is to avoid or reduce damage in minor to moderate earthquake. Let's not play with that major earthquake. Let's retain our life safety feature. So here, that is the criteria, that is the idea. Now, how do we reduce damage then? how can we reduce damage? We can reduce damage. Number one is provide very high capacity. Have you ever wondered when you go to some historical cities and then see those huge mosques, forts, palaces, which are still intact despite having seen through several big earthquakes? Where that comes from? That merely comes from the capacity. The capacity is so huge that the earthquake cannot do anything. But that is not the solution for our normal buildings. For our residential buildings, which are in thousands in numbers, we can't do that. Okay? But ideally, if you had infinite capacity, you could retain, you could avoid damage in any earthquake. Okay? Now, the next is now low damage technologies. That's where research is hitting. And few of them I have identified there: damage avoidance design or damage resistant design, external braces and dampers, base isolation. Let's look at them, what they do. First, damage avoidance design. It has got different names. Different people call it differently. Hybrid system, press system, rocking system, damage resistant design, whatever they call, the principle is the same. What are the principles? The principles are, we have precast components which are constructed in a factory. We bring it to the site, we assemble them together, put them together, and they have got holes inside through which we put our tendons, the post-tensioning tendons, and clamp it together in the site. Okay? So that's the principle. And it has got some really good features, which is self-centering system, means after the earthquake, whereas modern ductile buildings, they have some residual damage and residual displacement. You see them in a tilted position. That system would never do that. It would come back to its original position. That's what we call self-centering. Okay? So they have got few interesting features. So what is the criteria? What do we do there? The structural damage actually is associated with excessive bending. Like, for example, if you think about this, what does earthquake do? Earthquake doesn't apply any force. Earthquake simply moves your ground. I'm sitting here. If somebody moves my ground from here to Dunedin, I will not be damaged, but if you do very slowly, even if a building is transferred in a car, it will not be damaged. Why during the earthquake? Just because of small movement, it gets damaged, because it happens really fast. The acceleration is the key. You can imagine yourself sitting in a car, start your car, accelerate the pedal, your bum goes together with the car, your body wants to resist it, does this. So that's what happens in building. Your base is taken away by the earthquake, and the body of the building wants to retain its position, because it happens so fast. And in the process, it has to bend. And when it bends, it gets damaged, because that is what is happening. It is trying to bend, and on that process, the bar buckles, the concrete spalls, all these things happen. Now, if we avoid the need for members to bend, we can avoid damage. That is the principle of damage avoidance design. And how do we do that? We still allow the structure to deform, to bend, to displace. The top displaces in relation to the foundation. But that displacement doesn't come from bending. It comes from something called rocking. Now, that damage doesn't need to be there. What do? We smartly put some small sacrificial pieces. They will get damaged, which can easily be repaired or replaced after the earthquake. Whereas in that building, in that bridge or building, whatever it is, once that happens, when you send engineers to do that assessment, what the engineers would say, inside has been damage, the building is still standing, but the reinforcing bars have already yielded. And once they are yielded, they cannot be, regardless of how much you try, you cannot bring that back to its original position, original state. So legally, the owner is in a very strong position to say that, no, I don't accept this, you have to replace my building. And the insurance, even how big expert the insurance company's engineer is, cannot rule that out, because cannot argue against that. Yes, it is true. Once the reinforcing bar damages or yields inside, it is very difficult, if very close to impossible, to bring that back to original position. Okay? Whereas with this, we can definitely repair the building. Okay? So now, the external dampers, they provide the energy dissipation. The strength comes from the unponded post tension, that rod inside. And then, when the building rocks or when the column rocks, there will be a huge stress concentration in that point. So that is likely to be damaged. So you have to place a special detailing, special armoring technique to get rid of that that damage in that peak, okay? At that toe. So now we have tested this technology in the lab. We have done that for our bridge piers. We designed the bridge piers for the same level of seismic demand and constructed that according to our normal design, constructed that according to the damage avoidance design for the same demand, and subjected that to the same level of earthquakes. And at the end of the test, you can see the difference in damage. So definitely, subjected to the same earthquake, the damage is so severe here, not much, very much repairable, right? And we did that for building frames as well, not only for bridge piers. That is a small part of a multi-story building from second or third story. And we tested that, which resembles the actions that happen in a building in earthquake, during the earthquakes, right? And then if you look at it, we have got those features, which are rocking features between the joint between that column and all these three beams. They are just precast separately, brought to the site, tied together. And then when you apply that loading, they can simply open and close. Okay? So that's the technology. And we achieved all of this. However, now let's look at it. Effect on financial loss. What does it do? It definitely reduces damage, structural damage. But we are talking about loss. So in terms of loss, damage avoidance design has been proved to reduce structural damage. Hence, less loss from structural damage. That's one component. However, this method aims to reduce structural damage by rocking. It doesn't aim to reduce the displacement. The displacement is still significant. However, the column doesn't need to get damaged. But imagine in a building, you have got columns, you have got beams, and in between that beams and columns, you have got walls, partition walls or other types of walls. If your column deforms like this, your wall has to follow that. And when it follows that, because the deformation is large, it creates huge force. And the wall gets damaged. Because the damage to the wall, that is proportional to the deformation of the building. And this technique doesn't try to reduce the deformation. It just tries to reduce the damage of structure despite large deformation. In fact, deformation might even increase because the stiffness in some cases, some combinations might even further reduce. Okay? So because of that, you get more damage to the drift-sensitive non-structural components like partitions, facades, windows. And if you look at the acceleration will throw your objects, throw your contents away, and then create or cause damage to the content. So that the content damage depends on acceleration. Content damage, your ceiling damage, the floor acceleration decides how much damage happens to your ceilings. Okay? So if you look at that, the limited investigation that we have got so far, that indicates acceleration responses between the normal and damage avoidance design. They are comparable. So what that means is similar damage to acceleration-sensitive non-structural elements such as ceilings and contents. So when you combine all these three, what can you conclude? Therefore, in terms of total loss, damage avoidance design of structural system only may not offer much unless the cost of the structural system dominates the total building cost. Imagine a garage where you don't have partition wall, you don't need anything, you don't need windows, you don't need anything. You just have the frames and you just have floors and access to the car and parking facility. That is perfect for this damage avoidance design because 90% of the loss of that building comes from structural system only. Whereas if you apply this to normal building, office building, where your 80% of the loss is coming from non-structural and content, you will save very little, almost nothing. The only change it does is actually it makes the structural system easily repairable. Okay? So now, the second damage reduction technology that I talked about, external bracing or damping device. That is probably, I would rather show that. That is what we are talking about. We have got an example in several buildings, one of that buildings in Auckland. So those systems, those bracings that you put there, what does that do? Is it absorbs energy and adds damping to buildings in order to reduce seismic response. It is especially suitable for tall buildings, which cannot be effectively base isolated. We'll come to that. And retrofitting existing buildings is often easier with dampers than with base isolators. Okay? And There are several types of base isolation. You use viscous dampers, you use friction dampers, you use hysteretic dampers. There are several different types. I will not go through the details, but that has been applied in several buildings throughout the world. Okay? So now, but till now, we have not been thinking about non-structural or loss. Now, for the first time, we have started pondering about what it does in terms of loss. Let's look at that. Effect on financial loss. External braces make the overall system stiffer. As the system is stiffer, the displacement is small. So the building has to displace less. What that means is less damage to your structural system because the system doesn't need to deflect. Once it has to deflect, then comes the damage, right? Because it has to bend. And the drift-sensitive non-structural elements like partitions, facades, windows, they all will be less damaged. So a significant portion of the loss will be reduced. Now, due to increased stiffness, as you make the system stiffer, what that means is actually your acceleration increases. That is a simple fundamental dynamic theory. Okay? So the floor accelerations are higher. What that means is actually more damage to your ceilings and your contents. Okay? So therefore, external bracers may only give a small gain in terms of total loss reduction. In buildings where contents are very valuable or hazardous, such as hospitals, research labs, where probably the value of contents are many times greater than the value of building itself, the structure itself. So this option should not be preferred unless the contents are either isolated from the floor or secured properly to the floor so that they cannot be thrown away. Okay. Now, let's come to the last of the three of base isolation. Passive control technique to decouple a building from its foundation. We all know that. And base isolation does not make a building earthquake-proof. It just enhances the earthquake resistance. Okay? Regardless of how much you try, you can never make a building completely earthquake-proof. If an earthquake, a really big earthquake comes, nothing will stand. Okay? So our idea of the capacity design is okay because we don't have that control over the nature. Nature can turn in any size despite what we want. And then let's not try to control nature or predict nature. Let's try to control the man-made thing, which is the building. We make it. That is our slave. We tell it how to behave. We don't tell nature how to behave. Okay? That's what we do. And basically, that's what we are doing here. In base isolation, what we do is we simply make sure that despite how big the earthquake is, the building does not collapse in normal our design philosophy. Okay? Building might be damaged, but people are still safe. So these base isolation not suitable for all buildings, most effective for short or medium rise building on hard soil. Now, the normal concept of base isolation, ideally, if I put my building on ground with some marbles, with some rollers on it, ground moves. Regardless of ground moves, how much ground move, my structure would simply roll here and there. It will never get damaged. It will simply displace. But I will not have any control over how much it displaces. And that puts me in a very awkward position. Okay? So that's why what we do is we try to go there, but not as much. So what we do is we put a very flexible isolation between the building and the foundation or the soil, so that when the soil moves, this layer deforms and transfers only small deformational need to the building. Okay, so that's the idea, and that is done through different kinds of isolators. There are different kinds of isolators. I will not go through the details, but New Zealand is at the forefront of this technology. Okay, one of the early inventors of base isolation technique, Bill Robinson. He just passed away last year. Okay, he has got his own company, Robinson Seismic, in Wellington, and they produce a lot of isolators, different kinds of isolators. So now we have got these applications in New Zealand. Those load-bearing those isolators have been applied in Te Papa in Wellington, several buildings in Wellington, to be honest, and in Christchurch, the only building that we have so far yet, because I heard that there is second building being started, the St. Elmo Courts, that is being rebuilt with base isolation technology. But till now, we have only Christchurch Women's Hospital, which did very well in the last earthquake. So now, effect on financial loss. How does base isolation affect the financial loss that we get? So base isolation makes the overall system softer or flexible, okay? Which means that if the system is softer, the acceleration comes down. So acceleration comes down, which means less acceleration sensitive non-structural ceiling damage and content damage because acceleration is substantially reduced. Now, although the total displacement of the system increases, because the system is softer, then for the same saking, the overall displacement is large. But a major part of that overall displacement comes from the isolator, requiring the building to deform only little. So the requirement for the building itself is a lot small. And that makes, that causes a lot less damage to the structural system and drift-sensitive non-structural elements, partition, facades, windows. So overall, base isolation definitely results in a substantial reduction of overall building loss in an earthquake. Definitely a big thumbs up. Okay? Now, what is the cost implication? If you look at it, I just tried to search the internet and found that paper from Stanford University. They did some research and they found that this leads to, base isolation leads to an additional cost of $50 per square foot with their assumption, okay? Building owners and developers are reluctant to pay this additional cost. However, the benefits of isolation far exceed the initial cost of installing isolation, especially in today's society. That's what they think. Now, despite all this, why is not it happening? Let's hear what I think. Okay? What is stopping buildings from being retrofitted or base isolated? Who has to pay the extra cost for retrofitting the existing building or extra cost for new low damage building system? The owners or builders who build it, they have to pay. Do owners get higher rent for retrofitted or low damage buildings? No. The rent is decided flatly based on the per floor area. Do builders get higher price when selling retrofitted or low damage buildings? No, unless I am the buyer. I know the difference and I will be probably prepared to pay a little bit more. Okay? Do owners get any discount in insurance premium for retrofitted or low damage buildings? No. Do owners get punished for not retrofitting an earthquake prone building or not using low damage building technology? No. Are owners in any greater risk, financially or otherwise, by not retrofitting a risky commercial building? No, because they don't live there. They live somewhere else. They rent it out to shop owners or office guys, right? So they are not in any greater risk. If the building gets damaged, the insurance will take care of that. They simply have to pay the same excess, regardless of whether they retrofit it or not. So now, who reaps the reward of the investment? Insurers and tenants. Then why should the owners or builders spend any extra money? So the question comes, should not the insurance premium be in line with the risk posed? Yes, that is it. Because why you insure is actually you want to cover for the risk. So if something is well known to put you at less risk, why do you pay the same amount? So insurance company and to some extent the real estate industry, they have to play a great role. Because in current scheme, that's not working properly. There is no incentive for owners or builders to do any of that, to spend even one penny, extra penny in doing that. Unless like if I stay in that building, my life will be at risk, so probably I'll be forced. But in commercial sector, I don't stay in that building, I stay somewhere else. I'm trying to build a building for renting. No. Okay. So in conclusion, there is a mismatch between what buildings are currently designed for, which is life safety, and what the public expects, which is limited financial loss probably, in addition to life safety. Better communication is needed in future between structural and geotechnical engineers and architects and with public as well. All parties should be aware of each other's limitations and expectations. A major share of earthquake-induced loss in a building comes from damage to its non-structural components and contents. Hence, resources should be proportionally allocated towards development of damage-resistant technologies for non-structural components. This is a huge problem. The policymakers, they are not acknowledging it. Still, a lot of money is going into the, okay, because we got those damage in the walls, in the columns, but they were supposed to be damaged because the ground motion was so big, because we were aiming for life safety and that's what it has achieved. Okay? Because the problem is not with the structural capacity. If you want to it to not get damaged at that level of earthquake, then we have to simply increase the demand. Currently, we are doing for 0.3 factor. We have to increase that to 0.5, 0.6. Okay? So the proportional distribution of resources in developing different technologies is not there. In future, a loss optimization seismic design is needed, which explicitly aims to also minimize seismic loss in addition to ensuring life safety. To achieve the most optimum performance, the superstructure, foundation, and soil will have to be considered together in a system design approach. Base isolation appears to be the most convincing low damage and, more importantly, low loss technology, which reduces seismic losses of all kinds. Current insurance and real estate models will have to be modified to provide incentives for owners and builders to invest the extra initial cost to retrofit or base isolate their buildings. So finally, before I close, a closing remark, I told you the story about the Rajesh the engineer and Rajesh the citizen, the dilemma which I am facing. Now, my appeal is, let's give up our resistance to change attitude and work towards an approach that will require structures to meet the expectations of both Rajesh the engineer and Rajesh the citizen in future earthquakes. Okay? With that, I thank you for your patience and thank you very much. I'm happy to answer any questions you have.